Hello, I'm Layla, and I'm the RUAutonomous team captain and UGV team lead for this year.
Hello, my name is Jason, and I am the UGV team member.
Hi, I'm Jeff, and I am the imaging sub-team lead for this year.
Hello, I'm Arvin. I'm the hardware and autopilot team lead for this year.
And this is our flight readiness review for the SUAS competition of 2022. So the Jarvis aerial system is built on the MySky Dreamcast twin six-wing aircraft with a 10-amp battery and dual motors. It is autonomously controlled using the Pixhawk autopilot controller. The Pixhawk is connected to a suite of sensors like airspeed and GPS and communicates with the Jetson TX2 computer, which is responsible for communicating with Pixhawk and connecting with the Blackfly camera for image processing. The team uses the Ubiquiti rocket Wi-Fi station to transmit imaging data back to the central control server, and the telemetry is done through the RFD 900X modem with traditional RC control through the 2.4 GHz FRR Sky receivers on board the aircraft. The unmanned ground vehicle is custom designed and 3D printed and automated with a fixed tracer. It is dropped using a multiple servo release mechanism from the aircraft and lands with a custom cut and sewn parachute. For the ground station, it has two components, the autopilot ground station and the central control server. The autopilot GCS runs mission planner and is connected to another RFD 900X telemetry modem. The central control server consists of three components: imagery, obstacle avoidance, and interoperability. Its main clients are the manual ODLC image viewers and the mission control station, and the system monitors for both the UAS and the UGV. For our planned tasks and expected performance, we expect the Jarvis aerial system will fly autonomously, including takeoff and landing. We expect it to fly within 100 feet of accuracy for waypoints and stay within the flight boundaries at all times. After our extensive testing, we believe we are able to successfully conduct an autonomous flight with obstacle avoidance and achieve a medium level of accuracy with object classification and localization, as well as airdrop location. And we will go through the exact tests conducted over the next few slides.
So this is just, this slide basically covers the diagram of the process / timeline for our testing. It basically went through three phases, which was requirements testing for the hardware components, the unit testing for the software components, and then integration testing done through test flights and full mission tests. For the hardware components and the UGV, we basically verified through requirements testing that the specs and design met the restrictions of our aircraft as well as presented by the competition. And after they were placed in a fully built aircraft, and we did manual testing, like manual flights, to determine that the aircraft was functioning properly. In parallel with this, there was unit testing for obstacle avoidance, waypoint injection, and telemetry separately. And after unit testing revealed that these algorithms / programs could handle the edge cases present during the competition, we did CITL testing, which is basically simulating how the plane would react to the paths and random waypoints injected. And during this round of testing, we determined that RRT star was not a practical algorithm and that we're probably going with an artificial flow field or A-star variant during competition time. After making this determination and tuning the parameters through CITL testing, we did integration testing. We basically put it on test flights, tuned the controller on board, the L1 controller, and also tune the parameters to the real-life dynamics of the plane, and then full mission tests to determine what components function and further tuning. These are just diagrams to illustrate our metrics for what are realistic waypoints, what are difficult or stress test waypoints, and difficult arrangements of obstacles. These are the logs for our 5 primary fly days, and the first 3 fly days for waypoint accuracy were basically flights between shorter flights between 4 to 7 minutes, while the last 2 were basically flights from 5 to 10 minutes. And we examined whether the parameters were properly tuned, and after tuning them in the first 3 fly days, we got significantly higher accuracies on waypoints. And we also progressively increased the waypoints as well. For obstacle avoidance, we tested them as we did in unit testing. We randomly generated the obstacles and the waypoints, and we graded the average difficulty of these placements, and we progressively increased the obstacles as we went on. And as you can see, the collisions went down as we're tuning the parameters for our path planning algorithms.
Imaging tasks are done using the FLIR Systems Blackfly S camera, which is capable of capturing images at a resolution of 4096 by 3008. This means even the smallest targets can be captured by approximately 40 pixels, which is more than enough for running detection and classification. The Blackfly's general-purpose input-output capabilities also lets us to interface with the telemetry model directly, resulting in more accurate telemetry and achieve lower telemetry capture latency. Images are captured at 1 frame per second to allow for the transfer of the image and onboard classification to occur. The team will be using the Ubiquiti Rocket M as our primary method of communication with the central control server because of the multi-input, multi-output radio technology, which enables multi-path propagation and better overall coverage, helping us achieve better reliability. Object localization was done by plugging telemetry data from the drone and the pixel location of the detected object on the image into the localization formula developed by the team. This data is gathered from a telemetry snapshot the Arduino Micro gets from the MRO autopilot. Testing for our localization functions was done by manually measuring object distances, then inputting the values into the function to get a % error. With testing for 8 objects, we got an average of 89% accuracy. For detection and classification unit testing, the algorithms were tested on a set of 150 objects consisting of both real and simulated objects not in the algorithm's training set. For detection, 88% of generated images were correctly detected. However, more error was present in real images. The team developed a deep learning system for all components of the autonomous ODLC task. The system starts with object detection using a CNN model trained on MobileNet V1, which simultaneously detects and classifies target shapes. The team chose to use MobileNet because it is a lightweight model that does not use too many resources while maintaining high accuracy and speed. The detected bounding boxes are then sent to a script which analyzes the pixel values in the image, which classifies the required attributes of the object. Local orientation is then combined with telemetry to compute the global orientation.
So for the UGV portion, we decided to custom design and 3D print it. It is automated with a PixRacer and runs AutoPilot firmware. It is dropped using multiple server mounts and lands with a parachute. On the right are the components wired into the UGV, where the UGV acts like a storage to keep all of them intact together. Unfortunately, we're not confident about the performance of the driving and therefore will not be attempting the driving portion of the air delivery. On the bottom are the equations used to determine the drop location of the UGV and the water bottle, and that portion was successful during our full mission testing. So initially we decided to go with magnetic mounting for the UGV. However, after testing, we found that it actually interrupted other components that also included magnets. So instead, we decided to go with servo mounting, where through the use of a servo, the UGV will be able to drop through the opening and closing of the pins. Once the UGV is falling, it will be held by a parachute that will deploy. This parachute has 6 cores and 37 inches in diameter. We found that this was optimal through the use of MATLAB's Parachute Designer app. The picture on the right just shows the UGV mounted onto the plane using those servos.
Concurrently, we did full mission tests, and during the full mission tests, the early full mission tests revealed that air delivery and mapping were not working properly, in addition to autonomous flight and obstacle avoidance. But in the latter 2 tests, we determined that with the right parameters, we could get up to nearly full score on autonomous flight, obstacle avoidance, and timeline, which is what we expect during competition as well. But we did not get the same results for air delivery and mapping. We expect that to be 50% and 30% score during comp as well. But we increased object detection and classification, which we get roughly correct half the time. This is just a diagram to illustrate and visualize the results as seen before with respect to our confidence levels.